So today we're discussing random walks again, and this time to directly try to reduce randomization in a sort of black box manner. So yeah, we're doing randomization and random walks for quite a number of lectures now, hitting times, spectral theorem, Cheeger's inequality, and so last time we talked about expander graphs, we talked about the zigzag product, and we showed that you can actually somehow combine these amazingly and be able to do connectivity in log n space without randomization. Okay, so yeah, so expander graphs, they're like really well connected but really sparse at the same time. What's incredible is that they exist, as you'll discover on your homework. Uh, and it's actually easy to do connectivity on a expander in log n space because you can just enumerate all of the walks. And to take this basic strategy and apply it to a regular graph, or any other graph, we're going to take the graph and what we did was we gradually morphed it and massaged it, where, we would power it to try to improve the spectral gap, but then we take the zigzag product and make the degree small again, but we lose a little bit on the spectral gap. We power it, make it mix better, lose a little on the zigzag, but somehow it was a net plus, and we're ultimately able to actually basically take G and make it look like an expander, and then just do this kind of obvious thing. So, right, powering, the idea is that, okay, each step becomes two steps, so you get to mix that much faster. The zigzag product was like this crazy thing, but the high level idea is like, let's say you have a moderate degree 100 graph, and then you sort of have this pseudo number, random number generator that chooses one of 100 each time. So when I want to take a random step in my medium degree graph, and I have to pick one out of 100 neighbors, I use this pseudo random generator to pick it. The pseudo random generator itself is another graph. It's an expander over 100 vertices and very small degree like 5. So I'll take a random step in my small expanding graph. That'll take me to some vertex, like vertex 75. So in my original graph, I'll move to the 75th neighbor. Okay? And the other half of the zigzag product is just to make this operation symmetric. Okay, so that's the high level idea. Amazingly, that helps. So again, we just analyze like, okay, how does the spectral gap change as I take powers, and what happens when I do a zigzag product? And out comes like not that bad of a decay, or actually, sorry, a net increase in the spectral gap, as long as G itself doesn't have much spectral gap yet. Okay, so the 2 gamma G dominates the gamma G squared until we're done. So we're roughly doubling, and then we give back a little bit on the gamma H. Okay, so today we're going to sort of generalize some of these ideas. So we'll talk a little bit about complexity classes because that's the context in which these results are described. And we're going to have to talk a little bit about tensors of graphs. We've talked about that previously. And the idea is to try to do more efficient amplification, and we'll also have to talk about making large expanders. So, okay. Just some terminology. So, what's the definition of a language that's in polytime decidable? Well, first, who's taking a complexity theory class? Just curious. Or is taking concurrent counts as well? Okay. We have one pretty regularly offered, right? Was grad offered in the fall? When was the last time graduate complexity theory was offered? I know undergrad is right now. In the fall? Yeah, it's probably rough. It's what? Oh, okay. Maybe next spring or something. Yeah. It's offered fairly regularly. Okay, so it's in P if there's some deterministic algorithm to decide if some input is in the language. So this is the terminology I like to say, oh, the language, which is like some subset of all strings. Okay, so a language is in RP if you can come up with a randomized polynomial time algorithm that, uh, yeah, okay, hopefully I got this right. If x is in the language, okay, it'll say it's in a language is probability like 1/2. And if x is not in the language, it'll always say it's not in the language. Okay. And BPP is a little broader. So that means there's some randomized polynomial time algorithm. Oh, they stand for things. So I guess BPP stands for bounded error probabilistic polynomial time. If there's a randomized polynomial time algorithm that on input x, if x is in the language, it'll say so is probability at least 2/3. If it's not in the language, it'll say so is probability at least 2/3. Okay. So, you know, the way to think about this is that RP is one-sided error and BPP is two-sided error. Okay. The choice of constant 2/3 is arbitrary. It just has to be at least 1/2. 1/2 is not interesting because that's flipping a coin. So any constant bigger than 1/2 is basically equivalent. Um, good. Okay. So here are some questions. So it's easy to see that P is a subset of RP is a subset of BPP. Okay. And the question is, are these equal? Which at some level is saying, if you have a randomized algorithm for a problem, is there always a deterministic one? Right? So in this space, like the connectivity we did last time was a special outstanding case for a long time. That seemed really, really hard to do deterministically. Even randomized was a little bit. I mean, the algorithm is maybe simple, but it takes some nuance, right, in the analysis. So we don't actually know if these are distinct. I think that probably a lot of people, if they see a randomized algorithm come out, they believe there ought to be a deterministic algorithm. I think we would probably be more so in normal algorithms. There's some other settings like online algorithms and stuff that are like not quite in this framework. Okay, but in this sort of just like input isn't in the language kind of static setting, then I think, you know, if I see a deterministic version of something that existed in randomized, I'm like, okay, that makes sense. Not saying it's easy. It's often like really hard, and you have to really. It's like, okay, it'll be shocking, I think, if you can provably separate these things. Okay. Good, good. Yeah. Oh, the relationship between BPP and NP. Uh, oh, can we figure that out directly? Uh, so okay, let me ask you guys. Okay, so what is the connection between BBP or RP and NP, or is there any? So NP means the problems in NP. If X is in the language, there's a proof. There's some bit string Y, where that's polynomial in size of X. So I can run an algorithm on X and Y and decide X is in the language. So you need a proof. All right, let's focus on one-sided error, RP. Oh no, because NP requires uh, a proof. So there's a polynomial time verifier for NP, right? So NP means that I can check a solution is correct in polynomial time given a proof. Yeah, so okay, so L would be like I give you a graph and X, the graph is in the language if there is an independent set of size at least K. And then the proof will be the independent set of size at least K, which I can double check. So it's whether an instance satisfies basically a yes/no question. But let's look at just RP and NP. Does anyone see a possible connection? Because so what would be the proof, right? So if I'm claiming that RP is an NP, then I should be able to take something in RP and come up with a polynomial time verifier, that accepts the proof. Yeah. You can use the underlying random bits. So if you're doing something that takes randomized polynomial time, there's some bit string of random bits that the algorithm will use. So you can use that as a proof because it's one-sided error. Now BPP I'm a little confused by because that argument is not immediate. So I'm not sure. But I should know as the instructor of the class. This is absolutely a basic question. What is the relationship between BP and NP? And I encourage you to think about it and maybe Google it. Okay. Good. Good. Okay. Oh, you looked it up? Okay. Oh, okay. Nobody knows. Okay, good. So we're at the frontier. Okay. I was correct. Okay. But that's a very interesting question, right? Because like BPP doesn't seem that different from RP, but it wasn't hard for us to show that RP is a subset of NP, and yet we're a little struggling on, yeah. It's also not clear, BPP, you can also ask if it's part of co-NP, and if it's an NP and co-NP, which is, yeah, now getting more and more murky. Okay, so, oh, does that mean if, no, okay. All right, so let's look at a language with one-sided error, okay? So let's say you need m random bits to succeed with probability 1/2, right? And if I want to get the error down to delta, what would I do? Yeah, log, I think 1 over delta times. So we just repeat, just like we did like in the second lecture of class probably. Just run it and see if any of them say yes, right? It's one-sided error, so you just need one of them to say yes. And good. So how many random bits did you need in total? Not a trick question. Yeah, times m. And the question is, can you do better? Okay, that's the question we're looking at today. Can you do better than just repeating amplification by repeating? Okay. It's such a basic question, like, of course not. Okay, same thing for BPP. Okay, suppose I have something that has error probability 1/3 on both sides, and I want to get it down to delta. How would I do that? This is double-sided error. Okay. So we will do actually the same thing. We'll repeat log 1 over delta time. The constant will have to be a little bit bigger, and we'll output the majority. It's basically like the median trick kind of thing, right? So, and you just apply turnoff. It's 2/3 of them should be correct. So the odds of them only 1/3 should be wrong. The odds of half of them being wrong is going to go down exponentially fast. Okay, how many random bits do we need? Okay, just multiplying it up. And the question is, can you do better? All right, so this is what we'll show. Given an algorithm in either of these two regimes, okay, I can get error probability delta. So from constant error, whether it's double-sided or one-sided, from probability delta, for probability constant to probability delta, while A, increasing the running time by log 1 over delta factor. That's just like before. Okay. But only using log 1 over delta additional bits. So m plus log 1 over delta, not m times log 1 over delta. Okay. So you can actually use fewer bits. Okay. The slide says ideas. Any ideas for how to do this? This is like surprising, right? Because it's such a basic thing. How can you do better than just repeating? More random bits than truly random bits? No, it's just a bit. Yeah. Oh, I see. I see. Oh, okay. Um, okay, so it is true that for RP, if you just, oh, okay, so the question was, can you just terminate early? Like RP, maybe you'll get a yes after just 3 rounds, right? But the problem is if you have a no instance, you'll just keep going until, yeah. Okay, so maybe you start off with m initial bits, so you get one sample. And now with each of those additional bits, can you do something weird like do an XOR or some like weird, mechanism? I guess to some extent that's what we'll do. We will actually do something that initially starts with m random bits, and then afterwards the changes are not fully random. How do we come up with a scheme then to do, something where surely we create an expander? That's a great answer. Yeah. Yeah, that's it. Okay. All right. So okay. So I'm gonna make a massive expander with one vertex for every possible bit string. Okay. So there's 2 to the m vertices in this graph, and you're gonna start at a random one and walk around. Okay. And again, if I start somewhere in the middle, right? The next step is not very random. It's only one of 3 choices, right? None of these individual steps feel very random, but in the aggregate, you should be approaching the stationary distribution really fast, right? And this is something we're only looking at the aggregate eventually. So we're hoping that this trail of random vertices will come close to replicating a bunch of independent samples. All right, so to be clear, each vertex is one bit string. So I start at a random bit string, and you do a constant number of bits to go to another bit string, and that'll give you a different bit string, right? Constant number of bits, different bit string. And so each of those, yeah. It, it'll be a constant and it will be a regular graph. I'm not sure exactly what the constant and regularity is. So first of all, it's not clear that we can even make this thing because you need 2 to the m vertices. So we'll have to do something implicit like last time. And then out of that, there will be some constant degree and we'll have to do stuff like, yeah, actually, I think you're on to something that will come up. So we'll have to figure out how to construct this expander. um, which needs to be really big. And yeah, so each vertex will become fed in as a bit string. All right, so good. Okay, so yeah, some points. I think you guys have already made these points. We need to somehow construct this implicitly because M could be your running time, right? It's a polynomial time randomized algorithm each time if each step flips a coin. So it needs to be exponentially big, and we don't have time for that. Okay. Um, the next point, yeah, you need a lot of random bits for the first vertex. Each one after that is a constant number of bits. And yeah, okay, so we basically set all these things. All right, good. So that's our approach. So it's really building on ideas from last class. Like this might have come, I think the thing we're presenting today chronologically came before the what we did last class historically. Okay, good. So let's look at one-sided error. Okay, so let's call a vertex bad if the algorithm makes an error on the corresponding bit string, right? So maybe there's like maybe this middle region is the bad part. Okay, so these are the bit strings that would cause your vertex, your algorithm to incorrectly say it's not in the language when it's actually in the language. Okay, so if it's constant like probability 1/2 error, then I know that the bad divided by all the vertices is at most like 1/2, right? So okay, it's like okay, you have bad luck, and your first vertex is in the bad region, right? But as you randomly walk around, you're hoping you escape the bad region, right? As soon as you can get out of the bad, you'll get your final good instance. So, yeah, so it's only going to fail if the whole walk is trapped in the bad region, but the graph mixes well. We also know from Cheeger's inequality, all the cuts are pretty high conductance, right? So there's not really bottlenecks that you can get stuck in. Okay, in principle, we'll have to bear that out analytically. Okay, but if the graph is really expanding, you're hoping that a random walk is likely to leave the bad region. Okay. Okay. So what we're going to show is that so this is just a graph statement. So let's say I have a regular undirected graph, a spectral gap gamma. Okay. And I just have a set of bad vertices, and I'll let mu denote the fraction of bad. And suppose I do a random walk where the first vertex is sampled uniformly at random and the rest of them just walk around. Okay. The odds that all of the vertices are in the bad region will be 1 minus mu gamma to the t. Okay. So if mu is like 1/2, so this will be 1 minus gamma over 2 to the t. So it'll be e to the negative gamma over 2 t or something. All right. So we'll prove that. And okay, let me just. We're also going to prove something similar for BVP. So again, you can look at the bad vertices. Maybe that's the shaded region. Okay. And maybe the shaded region is at most 1/3. And again, you fail. This time, for two-sided error, you're not worried about being in or out of the region at any point in time. Because remember, your algorithm is doing a majority vote. You're hoping if B is much less than 1/2 of the whole graph, you're going to spend less than half the time in the bad region. So your algorithm is only going to fail if at least half of your random walk is in bad land. Okay, so we're going to prove this. This is the only graph in history that proves an expander version of Chernoff and not the actual one. Okay, if you give me a regular graph, okay, and you have this bad region, and I guess I stated it a little bit more generally, but okay, so I guess a slightly more general framework is imagine you assign points to all the vertices. Okay. Uh, which could be just 0 or 1, whether or not it's bad or not. Okay. Um, and let mu be the average number of points on each vertex if I just sampled them uniformly at random. Okay. So if you do a random walk, you're expecting to get mu points or mu coins per vertex. Okay. And so the claim is that, okay, the probability of being off by epsilon mu, epsilon your average, is at most roughly exponential in the number of vertices. It's a little screwed up in the top right corner compared to before because it's not going to be as clean as straightforward Chernoff because there's going to be some, technicalities from the graph. But morally, it's exponential in k. You're still getting epsilon squared k. That's sort of what you're expecting. Yeah, it really looks more like additive. Yeah. Uh, beta is, yeah, why is it there? Um, so if you set it to 0, I think it's just there for analytical convenience, but you can just set it to 0 and make it simpler. And then you get epsilon squared k, roughly. Yeah. I forget why. It's probably something I introduced. Okay. Because I can, yeah. Okay, so those are the two things we'll prove. We'll probably only do the first one today. Okay. And then, yeah, this is good because then you'll see part of the proof of the Chernoff bound. Okay. All right. So we want to look at RP. I'm just trying to escape the bad land. Okay. Um, and this is the bound I want to prove. The odds of the entire walk staying in B is at most this quantity. Okay. Good. Okay. So we got to prove this thing. Where should we start? Actually, don't totally remember. It's anyone have a suggestion? Okay, I don't think this is very interesting. Okay, let's let R be the random walk matrix. Okay, and at some level we want to do some kind of spectral analysis of R. It's going to have something to do with eigenvalues. So let's see. What's up? Okay. Okay, got it. So I'm really concerned in just how much probability mass is, that's not right. One sec. Okay, good. Okay, so what I want to show is that the probability mass is really going to leave B. Okay, so we're going to make this function, linear function P, where for each vertex, if it's in B, I keep the probability, and if it's not in B, I just drop it. Okay, so B is just dropping the entries outside of P is dropping the entries outside of B. Okay, and we kind of want to see, okay, we're hoping that when I look at the combination of PRP, okay, that's like 3 steps. The first step is I drop all the mass outside of B. Then I take a random step from B, I guess. And then I'll drop all the mass outside of B. Okay? And we're going to analyze this term. So this is some kind of like random walk inside B, and then there's a cliff where if you just fall off the cliff, you die. Okay? So I think need to is a strong word, but this is the approach we're going to take in the analysis. Let's see if the next line helps. Okay, so that's our setup. Okay, so let's look at this. So, okay, so I uniformly sample a vertex, right? And then I take t steps and I want to know what are the odds that the entire walk stayed inside. So for example, just take t equals 1 first, right? So PRP times the uniform distribution. So P times the uniform distribution is going to drop all the mass outside of B. So you just have your probability mass inside of B. R will take a random step. Some of it will stay in B, some of it will leave. Okay. And then you're going to apply the P function again, and it's going to drop all the mass outside of B. So just one PRP. So you start at the stationary distribution, so it's uniformly spread out, some in B, some not. You zero out everything outside of B because that walk has already left B. Okay. You take a random step, and then you zero out everything outside of B again because those random walks, that mass of random walks has left B. Okay. So you repeat that many times, and that's just taking PRP to a higher power. Note that applying P twice in a row is not a big deal. The second one has no effect. Okay. Yeah. Okay. So this is why this maybe partly answers your question, why we're doing this. Okay. So all right. So if we look at this, we can write it out like this. So n is just all ones times all ones because we have one for every vertex. And so that's at most PRP to the T. So this is just saying the biggest eigenvalue of PRP raised to the Tth power. Okay. So if we can show that the eigenvalue of PRP is small, okay, it's not necessarily 1 because PRP isn't a random walk because we're dropping this mass. R is a random walk, but not PRP. Then you just raise it to the Tth power. So I guess based on the claim, we probably expect like 1 minus gamma or whatever, mu gamma. Okay. Good. So yeah, that's our claim. Our claim is that the biggest eigenvalue of PRP is at most 1 minus gamma, mu times gamma. Okay. All right. So good. That will complete the proof. Okay. So we just want to analyze the eigenvalue of PRP. So we know that G is regular, so R is actually symmetric. So we don't even have to use the normalized random walk thingy. We just can directly analyze R. Okay, so we know from our spectral decomposition that R has some decomposition like stationary distribution comes first with eigenvalue 1, plus a bunch of eigenvalues, all, between 1 minus gamma and negative 1 minus gamma. Same degree. Now, right, and this is, so we're going to do the same thing we did last time. We're going to rip out a piece corresponding to the spectral gap, and then the remaining matrix has maximum eigenvalue at most 1 minus gamma. Or absolute maximum eigenvalue at most 1 minus gamma. Okay, so good. All right, so if we look at PRP and we plug in this stuff. Oh, okay, now I actually have to write. Okay, so we have P gamma over N. Let me write it differently. Gamma over N, P, 1x1s, P plus P R prime P. Okay. Okay, so this is P and this is the outer product of two ones, so this is like an all ones matrix. Right? So this will turn into applying P to this all ones matrix. Okay? Okay. And what do I know about this? What does P apply to the all ones vector? Sorry? Yeah, it's still a matrix. Yeah, so it's going to be like I'll write ones B just for it's only ones on the vertices in B, zero everywhere else. Okay, do we do anything to PRP? Let me just check. No. Okay. Okay. So now, okay, good. So, okay, I can just do this up above. So if we look at the eigenvalue, right? So initially it'll be like this, but we can use sort of this triangle inequality like this. Okay. So, okay. Uh, so let's look at this. What's the eigenvector of this? This is just a rank one matrix, right? So it has one eigenvalue of some non-zero value and everything else is zero. The eigenvector will be proportional to one's b. So what would be the eigenvalue? I guess maybe just to clarify it or make it simpler, what would be the eigenvalue just of this? Well, so this is not a normalized vector. Okay, this will be the size of b. One way to see this is that this is equal to the size of b times. So if you normalize this, you get 1's b over square root size of b. Sorry. If you normalize it to have unit Euclidean norm. Okay, so good. Let me put that out of the way. And okay, so this is gamma size of b over n. Okay. And what about this? Sorry? Split up all the norms, or here, let me do it slightly different. So you can write this as the maximum over all unit length x, p r prime p x. Okay. But P is just a diagonal matrix. There's ones in B and zero everywhere else, so it's equal to its own transpose. So I can flip that over. Px r prime px, right? So if you wanted to make this big, you're probably just going to choose x to have entries on B, right? Because px is just going to otherwise lose some entries for you. So let's say that x has only support in B and it has unit length. The maximum is at most 1 minus gamma. Because r prime has all its eigenvalues between negative 1 minus gamma and 1 minus gamma. Okay, so one sec. I'll come back to that in a moment. This is plus gamma, and what's size of b over n? We had called that mu. Okay, good. So why is p symmetric? Yeah, so the identity matrix, which is that diagonal for you or is that diagonal? This? Okay. So the identity matrix is ones, one, 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 one. P is identity on B, zero elsewhere. So it's ones and then becomes zeros. Okay. Good. So what did we show? We showed that, okay, so gamma U, plus gamma is what we got. Oh, good. Okay. Gamma U plus 1 minus gamma is what we got. And I hope this works out. 1 minus gamma plus gamma U. Okay, good. So that's what we wanted. Okay. All right. So spectral analysis, everything just falls out. Okay. Pretty slick. Okay. Good. All right. Let's do. So we established this. This one is done. So that's why a random walk will leave B. Okay. All right. Let's try to do proof of the Chernoff bound. Okay. So this one again is some kind of game where you have certain points on all the vertices, and so you're expecting a random walk to get the same average, and we're showing some concentration bounds, slightly uglier exponents. All right. Good. All right. All right. So how do we prove this one? So I think last time I taught this, I was like, oh, does everyone remember the first step of the Chernoff bound? But like, yeah, forgive me. Okay. So let's say you take a step for k steps, and then just generically say, okay, what are the odds it's bigger than lambda, and then we'll plug in for lambda later. So lambda should be something bigger than the expectation. Okay. So actually, does anyone know what the first step of the Chernoff bound would be? Yeah. Yeah, you exponentiate both sides and then you use Markovs, which would be come out to something like this. So I didn't write it out, so I guess you guys will never see that step. But you first exponentiate both sides. What is the probability that e to the fv1 plus fv2 plus fv? And so that's like really heightening and ramping up the gap. So if it's bigger, if it's much bigger than exponential, I mean, sorry, if that sum is much bigger than the expectation, then e to the thing will be much, much bigger than expectation. That's really going to ramp up the Markov's inequality. And you also, we included a coefficient t in front, just because that'll be convenient. So we'll choose t at the end. T is often like epsilon or epsilon over 2 or something at the end. Okay, so this is just Markov's inequality. So the main takeaway is that the Chernoff bound is just Markov's inequality. Okay. Now, if we're doing the normal Chernoff bound, do you know what the next step would be? Yeah. Yeah, so the normal Chernoff bound, those would be independent, the FV1 terms. And so you can turn that into a product of expectations, expectations of e to the x. And then you analyze these individual moments. And so what's kind of going on is that when x is a small random variable, like in a normal Chernoff, e to the x is basically 1 plus x. And then you can analyze it. So that's sort of what's going on. So you exponentiate at the beginning, where in the aggregate you're looking at a big average. So Markov's bound is on steroids, okay? But then when you break it up, you look at expected value of e to the individual x's. The individual x's are all small. So e to the x is roughly 1 plus x. And then it's easy to take the expected value of 1 plus x. You get the average and you add it back up, okay? Now, we can't do that here because we're not independent. And almost for lack of time, but we have a little more time. We won't finish today. But we will finish. So here we're going to do something, I guess, interesting. So F is going to be this diagonal matrix with, T to the vertex stuff. Oh, is this confusing? Okay, why did I write N instead of K? So that might be referring to vertices in the original graph, whereas V1 to VK are the vertices that came up in the walk. Let me double check. Yeah, yeah, okay. So this is not great notation. So V1 to VK in blue are the vertices in the random walk. V1 to Vn refers to the n vertices in the original graph. Okay, so clearly I should have chosen different variables. The notes have the same problem. Okay, so the claim is that this expected value, okay, over the k random step is exact. I think that should be k. Okay, that should be k. Yeah, training again. Have you guys seen this Europe's tutorial from 2016 or something about GANs? It's really great because an hour into it, somebody says, "Oh, I invented this in 1993." Uh, and yeah, it's a famous thing. Okay, shouldn't gossip too much on YouTube. Okay, so the claim is that the expected is going to be at most 1 over n times this thing. So what is this thing? So you start at, well, think of the n over here. You start at the stationary distribution. You collect some points. They're like coins. You take a random step. You collect some points. Take a random step. So it's like Mario's walking around getting all these coins. Okay. Um, and uh, except you're not adding up the coins. You're multiplying them together because that's how multiplying these diagonal matrices works. Right. So F is a diagonal matrix of e to the coins. Okay. E to the coins. So wherever you are, you get e to the coins. You take a random step. You get e to the coins. Random step, e to the coins, and they all multiply together. Okay. But because of the e, it's going to be e to the coins all added up. Okay. So, is that what I wrote out here? Yeah, okay. So, uh, FR is take a random step, collect coins, an expectation. Good. So if you do the K, you take K random steps. Bummer. Yeah, multiply it all together. Okay, so, sorry? Oh, that's true. So it doesn't include the first step. Yeah, FR to the 1 over n doesn't include the first step. There is a mismatch, but yeah, so we're only off by the initial factor of F, and that's just one, that's your initial coins. I think I only wrote these notes thinking it would be easier to read this way. Um, okay, yes. So to spell it out then, which can be written as FR to K F1's, let me write over N is it's sort of like this, the same thing as before, where you're collecting e to the f at each step, but also including the first step, or before the first step. Yeah. Okay. Good. Um, sorry. Okay. Oh, okay. We're over time. So, someday we'll do this. No, okay. We'll do it next time. So, but it looks like the next step is going to be similar to before. We're going to rip off a chunk corresponding to the spectral piece. And then we're probably going to be analyzing, FRF to the K, uh, and splitting it up as the first step. Okay, so that's probably where we'll pick up next time. Okay, thank you. Okay. All right, so we started this last time. We'll finish it today, and maybe you also get to start a little bit on the PCP theorem, which would roughly the Mount Everest of our class. So, right, we're trying to reduce randomness with random walks. This is sort of building off of what we did before that, which was trying to do connectivity in log space, right? And then we were doing these tricks with these expander graphs. So this idea of kind of like using, again, we know that for expander graphs, connectivity is actually easy. You can enumerate all paths, and sort of like a few bits can generate a lot of randomness. And so the intuition was, with the zigzag product was to use the expander graph as a sort of pseudo-random generator, right? And in the aggregate, a random walk in the expander, even if it's only using a couple bits each step, will actually look like a random walk, and that bore out in the analysis. Okay, so in a certain aggregate sense that only appears in the analysis, it does look like a totally random walk, and you get a win. So we're going to build off that today. Just to remind us, RP refers to polynomial time things with one-sided error. BPP is two-sided error. Okay, and so if you have a problem with one-sided error, then to reduce the error, the simple thing is like what we did with count min. We just repeat, and see if any of them answers yes. Okay. And so you're going to have to repeat log 1 over delta times to get your error down to delta. And BPP, you can amplify and improve your error similarly just by repeating. But now you have two-sided error, so you're going to want to take the majority vote. You take the majority vote, you apply Chernoff to that, and you'll still get this exponential decay. So the constant might be bigger, but it's a log 1 over delta overhead. Okay, so good. And I think we did the first one together. So yeah, so for both of these, we're going to show that rather than multiplying the number of random bits by log 1 over delta, which is you get what you do from independent, resampling, we want to just do m plus log 1 over delta. And the strategy was again based on this idea. So now if you have an m-bit algorithm, now a randomized algorithm that uses m random bits, okay, we're going to make an expander with 2 to the m vertices. Each vertex corresponds to one random bit string. Okay, so your first sample, you're going to pick a random vertex. It's a random bit string. And then thereafter, you're going to take a walk in that expander graph. Okay, and that's going to generate successive random bit strings. So there's going to be some kind of correlation or connection just because only certain bit strings can lead to subsequent bit strings. But we're hoping in the aggregate, it'll behave as if we were just completely independently sampling. Yeah. Okay, so can you somehow recurse or something or repeat? Okay. Not totally sure. Uh, One thing to note is, okay, so first is m plus log 1 over delta, which is already pretty good, right? Because you would need log 1 over delta to be bigger than m for it to even be a bottleneck. Now, if you want to get log 1 over delta down to log 1 over delta or something, first of all, if you recursed, you still have to pay the m plus, right? which on the recursive would probably be, well, could likely be log 1 over delta plus. Oh, for the initial. Uh, so I don't know if you can get it down to log 1 over delta by recursing. You can try though. And no, we'll give you like points or some imaginary, magical currency that you just make up as a. Yeah, we'll throw candy at you. Um, okay. Yeah. So, good. So the intuition is that this random walk and expander, although far from actually being a uniformly random thing in implementation, will still act like a uniformly random sample each time for the sake of uh, amplifying error. So good, good. So what we did last time when we fully analyzed for RP, if this shaded region represents the bit strings that lead to an error, right? You only make a mistake if you first sample in the bad region and then your random walk stays inside. Okay. So we analyzed this and showed, okay, you're probably going to escape any bad region because the graph is expanding. And that's what we did. Well, okay, I guess we'll just keep following the slides. BPP, which is what we have remaining today, we want to argue that, okay, even if it's not really just about being in the bad region the whole time, our error only makes a mistake if it's in the bad region most of the time. Okay, and the bad region should represent, say, a third of all the things. Okay, so you're hoping that, okay, the random walk is going to get outside the bad region and spend a lot of time outside the bad region. Yeah. Okay, so you asked, why do you need to do anything random? That's an interesting point. Well, we can double check with the analysis in hindsight. So that's at least a good suggestion. Why not just always start at this corner if you're going to get anywhere pretty fast anyway? So that's not a bad idea. Okay. Yeah. Yeah, that would be a good homework problem. Yeah. Uh, okay, so this is where teachers can be clever. So if you think it's too good to be true, then I would instead pose the question as, consider this suggestion, what goes wrong? And that would be the homework exercise. Yeah, that might be good to tease out. But it's an interesting idea, right? Pick a particular vertex. If I took to the limit this idea that I'm going to converge to uniform stationary distribution anyway, then who cares where I start? That's the idea, right? Yeah. Okay. Good. Good. Good idea. Um, yeah, and I'll come back to this because this is what we're going to focus on. But we're going to prove some kind of expander turn-off thing, where there's some kind of concentration. Okay. Now, okay, I'll just remind you what we did last time. So for the RP one, what are the odds you always stay in the bad region? We just ended up doing kind of the spectral analysis that we've been doing for like a couple weeks now. So I think the first step, okay, one thing clever was rather than analyzing just the random walk matrix R, we included this, I guess, projection matrix where we drop the probability mass outside the bad region. Okay. So now PRP is you're walking around, but you're just killing off everything that leaves the bad region. And over time, you're just left with how much probability mass is left in the bad region. So that's what we did. And we just analyzed the spectrum this is the kind of thing we've done a couple of times now, right? We wrote out the spectral decomposition of R because R is symmetric because the graph is regular. I rip off a chunk corresponding to the spectral gap. I can calculate explicitly the projection on that first eigenvector because I know that the bad region is at most half, or mu is the variable we have for it. So this I can compute explicitly. This remaining residual term I already know has small spectrum because those are the smaller part inside the radius, and you just put all that together. Okay, good, good. Um, right. So that's that. And what we had started to do was this kind of Chernoff-y looking version. So the way we formulated it was, imagine that every vertex is associated with like a number of points. Imagine like Mario. Okay. And so, as you walk around, there's this expected number of points you get per vertex, right? So mu is the expected value of f of v, where f is the number of Mario coins on vertex v. Okay. And you're saying, okay, as I walk around for k steps, what are the odds that I deviate from the average number of Mario coins? And you get this Chernoff bound looking thing where you get epsilon k in the exponent. Actually looks more like additive Chernoff because of the dependence on k. I think it's hard to get a multiplicative one. I think I've tried, but I forget exactly what happened. Okay, good. So that's that. Here's where we kind of left off. So, okay, so the first two steps are kind of standard from Chernoff style proofs, for those with standard backgrounds in Chernoff bound proofs. But you take, you start with, okay, what are the odds that the sum is at least lambda? For some value lambda, we'll choose later. And you exponentiate both sides first. Okay. And now you're saying, okay, what are the odds that if lambda is much bigger than your expectation, then okay, you're unlikely to exceed lambda. But Markov, you can kind of ramp up our Markov to say, okay, uh, if x is smaller than y, then e to the x is much, much smaller than e to the y, right? Because you're going to exponentiate things. And then you apply Markov, and you're kind of getting a little extra juice this way. And, okay, so how do we actually model this? So we're left with this moment, expected value of e to the t of some parameter to be chosen, and then the sum of Mario coins in the top right. Okay. And we want to do some kind of analysis. And so the first claim is that I can actually model this as sort of like FRF to the K, where F is going to be a diagonal matrix with the exponentiated coins. Okay. And so the idea is you're at the stationary distribution. So we're not actually directly analyzing the sum, we're analyzing e to the sum. Right? So you can think of that as e to the fv1 times e to the fv2 times e to the fv3. So at the first step, you're at some distribution, and you just get, e to the expected stuff. Okay, so you apply f once. You take another step, and now you're at some distribution over v, and you get e to the coins, and you multiply that in. Okay, which is going to be adding in the exponent. So each f in the middle is when you're collecting the coins in this kind of multiplicative way, and an r in between is taking another step. Okay. So the expected value of this thing is going to be, okay, so this one's on the right, one's over n is the stationary distribution to begin with. Okay, and ones is just adding everything up, doing the expectations at the end. So for all the trails of all the random paths. Okay, so, or you can imagine like, so you start at a random vertex, you get the coins, e to the coins. Then you pick another random vertex and you get e to the coins there, random vertex, e to the coins there, random vertex, e to the coins there. Now things are only happening expectations, so it's more like the probability goes down and down and down for every possible trail. But along the trail, you're multiplying the coins, but the probability is going down and down. And then it all kind of gets summed up at the end. Okay, so this identity is very helpful because now from here, it's going to be somewhat analytically more straightforward. Okay, but I think a key is to first model this correctly. Get a nice clean identity. Okay, good. All right, let's keep going. Yeah. Yeah, and that's represented by the ones on the right, which should be divided by n for the stationary distribution. Okay, good. So we're going to do, I guess, something similar to start as before. We'll rip out the small radius and the part that juts out from the spectral gap. And let me just make sure I do this correctly. Okay, so I guess we're going to find it. Okay, so, oh, good. We have something to erase. Okay, so what we're going to do is we're going to look at f to the 1/2 r prime f to the 1/2. Because we're really interested in like FR, 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 FR. And so we're going to break that into a bunch of products of square root F, R, square root F multiplied together. And then there's some extra square root F's to deal with at the end. That's okay. Okay, so I guess the claim is that F to the 1/2 R prime F to the 1/2 is at most epsilon e to the T. Where epsilon is 1 minus gamma. Okay, good. So that really represents the second largest in absolute value, right? Okay, so why is why is this so? Okay, let's see. Yeah, how can we prove this? Uh, it's going to be it's really the maximum eigenvalue. Sorry? Okay, let's just do this a little slowly. So for any test vector x, so let's say x has unit length. Okay. Uh, Let me group the terms a little bit like this. So f is diagonal, so you don't have to transpose anything. And this thing is at most, and I think this is what you're saying. Sorry. Epsilon, the norm of f to the 1/2 x squared. Okay. And then f is a diagonal matrix where the entries are, yeah, they're between like e to the 0 and e to the t, because f of v is always between 0 and 1. Uh, so this is at most epsilon x squared. So the biggest eigenvalue f to the 1/2 is really e to the t over 2, but it's squared, so that's where the t comes in. All right, so that's that. Nothing too special. So epsilon is just coming from the radius. E to the t is coming from the biggest entry in f. Okay, good. Good, we're doing great. All right, and now here's the next claim. Yeah, okay. All right, so let's parse this slowly. So this is a matrix. Diagonal matrix, the square roots of the coin values, exponentiated coins, times the all ones matrix, times the exponentiated coins. And on the right, we have something kind of semantic. The expected value of e to the, right, it's the expected number of coins if you just chose one uniformly at random. Okay, so left-hand side looks analytical. Right-hand side is something that makes sense. Okay. How can we do this? I guess this analytical stuff is just hard to stare and come up with suggestions. Yeah. Uh, t okay, let's try this. Okay, so this, just because the inner product has sort of this nice form, I mean, the inner term has this nice form, um, this is the same as f to the 1/2 all ones, outer product f to the 1/2 uh, all ones. Okay, so this is just sorry, I drew an extra caret for no reason. Um, okay, so what's this? This is just a rank 1 term, right? So this is just a rank 1 matrix. So that means the eigenvalue, right? We're interested in the eigenvalue, is just whatever's the Euclidean length of this vector, right? So this is the eigenvector, but it's not normalized. So we just have to figure out how much it's scaled up by. Okay, so rank 1 matrices, the only vector in its representation, that's the first eigenvector, and whatever the length is will tell you its eigenvalue. So now let's look at the length of the thing. F to the 1/2 all ones, and we'll eventually take the square root. Oh no, it should be squared. Okay, that's fine. So for the first eigenvalue, okay, so this is, you can write this as all ones, F all ones, right? Initially it should be F to the 1/2 all ones, inner product F to the 1/2 all ones. I brought one of those F to the 1/2s over, square root F's over. So now you get this. Oh, off by a factor of 10. Yeah, sure looks like it. Okay, I agree. Something like this. Okay, there's an extra factor of n here. Did we do this? Oh, we're going to be able to get rid of the n in a moment because the n will come out of the first eigenvector of R. Okay, good. We'll get rid. Okay, life's okay. Okay, so there is an n here, but it will, yeah. There are some typos in the notes. Okay, good to know. All right. Okay, so now we put everything together, right? Right, so that n is going to annihilate with this n. So let me put this n back in here. Okay. And okay, so this thing is at most uh, gamma over n times this thing plus this thing. Am I doing that right? Okay. I think we just start plugging in gamma expected value of e to the t fv uh, plus epsilon e to the p. All right, good. Making progress. Um, oh, wait, I should do a little more, I guess. Okay, so now I want to deal a little bit with this term. So, okay, so I want to extract out something related to the expected value of f of v. This is something we haven't done before, but we would have done if I had done the proof of. Okay, so so I know what the expected value of f of v is this value mu, right? And it has some meaning from the outside world. And I want to somehow sneak mu into the picture. The problem is, yeah, it's e to the tfv, right? So how do I get rid of the exponent? Yeah, so we know e to the t is roughly 1 plus t, right? So we're going to make sure t is between 0 and 1, and f of v is already between 0 and 1. Now, e to the x is not exactly 1 plus x. It's always greater than, but I really want is e to the x is less than or equal to 1 plus x plus something. So you know that e to the x is exactly equal to 1 plus x squared over 2 plus x cubed over 3 factorial plus x fourth. So if x is small, like at most 1, the x cubed over 3 factorial, the x4 to the 4 factorial, they go to 0 very fast. Okay? So if you go from like roughly 1 plus x squared over 2, and if you just you just round up kind of and say 1 plus x squared, e to the x will be less than or equal to 1 plus x squared for x up to maybe log 2 or something. You can work it out. Okay? So it's saying that it's almost 1 plus x squared. So yeah, do I want to do that one or do I want to do something simpler? Yeah, okay, let's do that one. Okay, so this is less than or equal to gamma of expected value of 1 plus TFV plus T squared S squared FV. Okay, because e to the x is at most 1 plus x squared. Okay, for x at most 1. And so this is mu. Oh, the t's look like pluses, right? Yeah, okay. Um, this happens every year with the turn-off bound. Okay. Uh, yeah. Okay. Yeah. Okay. So the expected value f of v is this parameter mu. How can I deal with the f squared v? Huh? Yeah, just upper bound one of them by one, so you get t squared mu. Okay. So so this is less than or equal to gamma. Oh, I've gone back colors. Uh, 1 plus t mu plus t squared mu. Okay. Yeah. Just have to write more slowly. This is legible. Okay. And good. Good. And I think what we want to do is, yeah. Okay, good. Good. Um, okay, and meanwhile, this one, likewise, is at most epsilon plus t epsilon plus t squared epsilon squared. Oh no, sorry, there's no epsilon squared. Something like this. Okay, so what happens when we start putting everything together? Did I run out of space? I did, okay. I don't know why I thought that was enough space. Okay. All right, let me just start putting things together. So we have, all right, epsilon plus t squared epsilon plus 1 minus epsilon is gamma times 1 plus t mu plus t squared mu. Okay. I'm going to set, oh, my t's and pluses begin the same again. I'm going to set t to be epsilon just to start killing things off. So you're getting, I'll write it out first, 1 plus t epsilon plus t squared epsilon plus, oh my eyes, 1 minus epsilon, 1, oh wait, I was going to replace the t's with epsilons, okay. Like, okay, the good news is that we don't have any t's. Uh, epsilon cubed plus 1 minus epsilon, 1 plus epsilon mu plus epsilon squared mu. And what I wrote, you guys can double check, epsilon plus epsilon squared, mu plus epsilon. Did that work out as nicely as I claimed in the notes? Okay. Oh, I see. Yes. Yes. Okay, good. Um, and then we're going to flip this back into exponent land. Okay. Now, maybe one comment I'll make is just because this intuition also applies to the real Chernoff bound. Okay, it has something to do with the exponent. So we applied uh, the exponent at the beginning when you're looking at two pretty large quantities, right? You had lambda, which is supposed to be like at least the sum of the FVs, and you had the sum of the FVs on the other side. So we exponentiated at the beginning two large quantities and sort of amplified Markov's inequality, okay? But then because of things like independence, or in this case we have something like independence, you have to break it down through the spectral theorem. You end up doing this, you look at e to the, t something for individual small values, right? E to the x for small value of x. So there we go back and forth between e to the x and 1 plus x, plus x squared terms, and lose almost nothing because e to the x is basically 1 plus x for x small. Okay? So we get to sort of take advantage of, the usual, oh, exponents are big when the terms are large, and that's where you're getting a lot of power from. But then we can go back into kind of linear land and get expectations and stuff out of it. Because you lose almost nothing when you're going back and forth between e to the x and roughly 1 plus x. Okay? So you can decompose the individual components of the sum on this small scale, but also benefit from the large scale in that first step. That's sort of the high level hand wavy intuition. Okay, so right, we're almost done. So we've reached this stage. So now what? Okay, so now we've bounded what's the moment e to the t fe1 plus fe. We plug this thing in. Um, right. Uh, okay, so now we look at this thing, 1 over n, uh, all ones, frf to the k, all ones, kind of thing. And we write this as square root f ones, square root f r, square root f to the k, square root f ones. Okay. Don't look too excited now. Um, and uh, and so you're going to get 1 over n times, I guess, the right, and then you're going to get this term we just looked at before, and then this eigenvalue, uh, which unfortunately was written in terms of t's again, but we can replace that with epsilon. And this we already have looked at before. Uh, is there a factor of k? Yeah, it should be in this exponent, like there. Uh, and then there was an n here, so you're left with uh, sorry, what am I trying to call? Okay, expected value e to the tfv times. Okay, this is just coming out very gory. Uh, in this term itself, this is at most 1 plus big O. Okay, one sec. I'm kind of losing the thread here. For lack of space, I don't know why I didn't give myself more space. Oh, I did right there, didn't I? Okay. Let me just address this here. So if I look at this term, this is a most expected value of 1 plus, say, 2 TFV. Okay. And we're going to choose T to be epsilon. F of V is at most 1. So this is at most 1 plus 2 epsilon. Okay. And so this will become a 1 plus 2 epsilon. And it's about as bloody as it looks. Okay. Oh, is that it? Okay, one sec. All right, let me. So if you just believe me, the math got a little messy. I didn't allocate my space correctly. Okay. I promise, and by promise, I mean I'm wrong with 50% probability, that this is actually what we did. Okay, you plug everything in. If I copied and pasted things correctly, and I managed my space better. Okay, this is what we got. Now we go back to the top part of the proof where we first applied Markov's. Okay. So this quantity here, see, now you know why I didn't want to do Chernoff in class. Okay, this is at most, some constant factor, not a big deal. Uh-oh. Okay, this is not going well. Uh, Not good. Okay. Oh, I included the one. Okay. It's just getting worse. This thing, uh, minus mu. Oh no, minus epsilon lambda, because T is epsilon. And, what am I looking at? So, oh, I just said epsilon lambda. And, right. Right. So I think lambda we're going to set to this value. Oh, no, we're going to set it to something bigger than this. Maybe you can replace for lambda the 1 plus epsilon with 2 epsilons or something. Okay. So then you're going to be left over with, what are you going to be left over with? You're going to be left over with something like uh, e to the negative epsilon squared over 2 k mu. So if I set lambda to be equal to 1 plus, say, 2 epsilon, K mu. So K mu is what you expect the sum to be. And instead of doing 1 plus epsilon, I made it 1 plus 2 epsilon to have a little extra padding. Okay. So the first 1 plus epsilon of this is going to kill off these terms in yellow, but you're going to subtract, you're going to still have the left epsilon left over to subtract. So you get epsilon squared over, there's no over 2, just epsilon squared, K mu. Epsilon squared K mu, and you give back, oh no, maybe we'll do this different. Uh, Maybe we'll make a Q plus epsilon or something. Lambda's whatever we want. Well, okay, so lambda was a parameter to be determined, and this is us trying to determine the right one. And me finding I don't have the dexterity to write enough numbers in the top right corner of the of the exponent. Uh, so I'm just going to set lambda to be big enough to cancel out these terms and have a little bit left over on the negative side. Oh, well, not if it's cursed. Um, yeah, I think that's okay. The point is you set a lambda to the right value, and I've lost the plot, and I guess we chose lambda to be roughly epsilon mu plus beta, and then this will come out, okay, up to some constants. Okay, good. So that's the proof of this more complicated Chernoff bound. The regular Chernoff bound is actually the same thing. We would just skip the spectral analysis in the middle. Okay, so luckily we've now covered all our bases. Yeah. Yeah, no, you can, but like it just takes 5 minutes. Uh, yeah. No, you can do it correctly. It's done more correctly in the notes. Yeah, yeah. But you're going to set lambda to the correct value. Okay. So what's the moral of this? I think the moral of this is, so I think this is the hard thing to analyze, okay? The exponentiated e to the sum of coins that you're collecting, okay? It's hard to analyze because it's not independent. So normally in a Chernoff bound, you can just break it up directly, right? And then once you break it up into individual expectations, then you just do that, oh, e to the x is basically 1 plus x trick and you're done. Okay, that was relatively easy, although the calculations went off the deep end because I just didn't have enough space. But here we're doing a random walk through the expander. So f of v1 has a lot to say about f of v2, a lot to say about f of v3. Okay, so it was really important to pull out this FRF thing, right, and be able to write out this moment exactly as this. FRF to the K. So you haven't lost any of your independence or dependence there. That actually captures all the dependencies of the walk, right? But even with all the full dependencies of the walk, we can start breaking out and doing some spectral analysis. And the spectral analysis will say, okay, even though you have all these dependent things, it's a random walk, the eigenvalues are looking at things in a certain aggregate way, right? And then you get the thing you want. Okay, so really the hard part or the interesting part was just dealing with this moment. Okay, and normally that's easy to break up because of independence in a regular Chernoff setting. We don't have that here, and so but luckily we had this very clever identity of this FRF to the K, and that we can directly analyze.